To give you a sense of what's happening, we're sending this infrared pulse onto the tip sample area. That infrared pulse, if it is absorbed by the surface, is going to cause the surface to heat up and expand and provide a mechanical force onto the AFM probe. Again, we're going to be using that AFM probe as a pickup and using the resonance frequency of it to amplify the signal that we're detecting there. So even though it's very, very small, we're able to detect it readily. And it turns out that the magnitude of this force is directly proportional to the absorption coefficient, which is what you measure through FTIR. So just by looking at the maximum of that ringing signal in the cantilever, we can measure out a spectrum on the size scale of an AFM probe that correlates beautifully with FTIR. So we talk about that it does correlate. What exactly is happening from a loose mathematical perspective here? So with every infrared laser pulse that arrives on the tip sample area, we introduce heating into the sample surface. Now, this heating is very, very small. It's on the order of a few degrees Kelvin. But what happens is as the pulse arrives, we begin to heat the sample up until the laser turns off, where the sample has reached the maximum temperature. It then undergoes a relaxation back to room temperature before the next pulse arrives. And so in the time that we have this pulse arriving, we're introducing a change in the size of the material, this delta R here. And this delta R is dependent on constants, depending on the elastic properties, the coefficient of thermal expansion, but also that maximum temperature value there. This maximum temperature value is then dependent on the pulse duration, the heat capacity, and the absorbed IR power. These pulse duration, heat capacity, and so on are kept constant during the measurement, so this is also a fixed value. So we're only looking at this change in the absorbed power. And this absorbed power here is determined by the absorption coefficient of the surface. So the imaginary part of the refractive index, which is what we measure when we measure FTIR. So just like that, we get this change in the size of the material, which is directly proportional to the change in temperature, the absorbed power, and what is measured through FTIR. So we get this very, very beautiful relationship between what we can measure through AFM-IR and FTIR. So the proof is always in the pudding here. And so this is an example on a nylon polymer taken with resonance-enhanced AFM-IR. And what we see is really, really beautiful agreement in terms of peak positions and band ratios between AFM-IR and FTIR. So in the case of a nylon polymer, one thing that we can see is we see the main chemical functionalities. So we see the amide1 and amide2 vibrations. We see the NH vibration up here, as well as CH stretching vibrations over here. But when we look at these smaller, lower energy vibrations, these are descriptive, and we call this the fingerprint region in an infrared spectrum. And it corresponds to a lot of the ensemble vibrations that exist in the whole system. And what that points to is that not only is this a nylon or a polyamide structure, but also the actual chain length within the polymer, so that it's nylon 6 specifically. And so we can use this and put it into a spectral database, such as Wiley's Know-It-All. And when you do that, you can get this really nice hit between the spectrum that we're collecting here and nylon 6. So this really is a useful chemical identification tool on the nanoscale. To further contextualize it among other chemical identification and molecular and elemental identification techniques, I want to use the SMART chart from Evans Analytical Group, a Eurofins company. So they have a photothermal AFM-IR tool, the Dimension IconIR. And in that, they have mapped out the space that NanoIR covers that is unique among other chemical and elemental characterization techniques. So here we can see FTIR with its micron scale spot sizes. We can go down to XPS or Raman or TOF-SIMS, as we've talked about already. But the unique space that NanoIR and AFM-IR specifically cover are this molecular information with a sub 5 nanometer lateral resolution, sensitivities down to monolayers of material, so less than 1 nanometer thick of material can be readily detected. And it can work in ambient conditions, so no UHV or high vacuum needed, while also being fully correlative with other AFM techniques. The beauty of using the AFM probe as a detector means that the quality and the strength of the AFM fundamentally determines the signal to noise and the quality of your IR mapping and spectroscopy as well. So what that means is the better your AFM is and the more functional your AFM is, the better it is at AFM-IR too. So it's able to create a no compromise system that does both things as well as it would individually. That said, there are some considerations to take in when we use the AFM probe as a cantilever. As I said, we're using the resonance of the cantilever to enhance the signal so that we can detect down to 1 nanometer thick or smaller materials where we're detecting single bond radii and vibration. And what that means is you need to be mindful of changes in the cantilever resonance frequency. And so the example I have here in the top right is just when you move from a hard material to a soft material,